In this lecture, we're going to provide an overview of dynamics, dynamic analysis with a specific focus on linear dynamics. And so when we talk about dynamics, what we're dealing with here is that branch of mechanics dealing with the accelerated motion of a body. Contrast this with the previous module where we focused on statics, objects in a state of rest experiencing zero acceleration. And as it was with the statics case, the foundation for dynamics once again is Newton's second law, and we'll step through Newton's second law and develop an understanding of how this is going to be the foundation for a dynamic analysis. As indicated, this lecture will focus on linear dynamics, and so those are objects experiencing a change in position in a linear sense, straight line motion, as opposed to rotating bodies. And so when we start with the foundation here, an expression of Newton's second law, as you see on this in this equation, we have the sum of a number of forces that are acting on a system is going to equal the mass of that object or that system times the acceleration of that object or that system. And so with the equal sign, the elements on the left-hand side will express the mechanics associated with that object that is equal to what is on the right-hand side. It's just that the two branches of biomechanics are depicted on either side, but both will yield the same outcome. So when we talk about Newton's second law in terms of force equals mass times acceleration, that is referring to objects or systems experiencing linear motion. So lowercase a is the symbol for linear acceleration. But when we talk about rotating bodies, the rotational or angular counterpart to F equals ma are the sum of the moments of force, or the sum of the torques acting on an object, a rotating object or system, is going to equal I times alpha, which we'll define here shortly. And so as this was illustrated in a previous module, if we separate these equations to the left-hand side and the right-hand side, the left-hand side depicts the kinetics branch of biomechanics, which is a focus on the forces and the moments of force that result for rotating objects. Now, if we're dealing with objects that or systems experiencing linear motion, then we wouldn't deal with the lower equation. So that the left-hand side depicts the kinetic side, the right-hand side depicts the resulting action of the sum of the forces or the sum of the moments, which will cause an object of having a particular amount of mass experiencing a change in its velocity, a time rate change in its velocity, which is acceleration. And so the beauty of Newton's second law is that the equal sign creates a marriage between the two branches of biomechanics, be it the kinetics branch and the kinematics branch. So just as a reminder, in terms of M and I, it's important to know that A is linear acceleration, alpha is angular acceleration, and these are the two kinematic measures. The M and the I are multiples for these two kinematic variables, and so they represent the multiples, or you can even think about them as potentially a leading coefficient. That doesn't fit the exact term, but what we're doing here with acceleration, whether it's linear or angular, is we have to consider the inertial properties of an object or system. So generally, inertia refers to the resistance of an object to its change in its state of rest or uniform motion. So an object could be in motion, experiencing a constant velocity, but to change an object's constant velocity, a net external force or a net moment of force if that object is rotating would have to overcome that inertia. So in the linear case, mass is the inertial term that presents a resistance to a change in an object's state of rest. So essentially here, an object with more mass will have greater inertia. Therefore, the object with greater mass, which in turn has greater inertia, will be more difficult to move from a resting state. In the angular case, I replaces the m, and I refers to something called the moment of inertia. Mass is just one variable in the determination of I as the object's inherent resistance to a change in angular motion, but there are other factors involved. It's the other major factor here that we'll discuss in a subsequent part to this module relates to how the mass is distributed among that object, about that object. But mass is certainly one of the considerations here. So an object with greater mass is going to be essentially harder to rotate. Okay, now one last point here. If we are provided with acceleration data, so from an experimental perspective, if we were collecting motion data and wish to estimate the forces that are generated to create that acceleration, that process is referred to as inverse dynamics, sometimes referred to as backwards dynamics. Backwards because as we typically read equations from left to right, we perform the analysis by starting with information related to acceleration, and we calculate backwards to get an estimate of the forces that are in existence that would create that acceleration. If we somehow had information on the forces or the moments of force, so inverse dynamics is applied in the linear case, it's also applied in the angular case as well. That's one more important point to make here. So inverse dynamics is the process of estimating forces from kinematic information, from kinematic data. Now, if we have information related to the forces generated on a system, can we predict what the kinematics would be? And from an analytical perspective, yes, we can. And that process is referred to as forward dynamics, where we read equations left to right, and essentially we're reading them in a forward direction in this analysis. And so if we had information obtained in the laboratory related to the forces acting on an object, or the moments of force acting on a rotating object, will we be able to generate a prediction of what the kinematics would be? And yes, we can, because of Newton's second law in what we call forward dynamics. But the inverse dynamics approach in the field of biomechanics, particularly human biomechanics, is the one that seems to be most often used. And once again, we can never forget our frame of reference. This is going to allow us to make interpretations to the overall problem by decomposing all of our vectors, expressing everything with respect to x, with respect to y, counterclockwise rotations as positive. Okay, so in terms of performing a dynamic analysis, an analytical dynamic analysis, there we follow some unique steps here. The first thing to make note of is that our approach is identical to that of a static analysis in terms of drawing diagrams, establishing a frame of reference, using the equations of Newton's second law, with the exception that we have to add in acceleration. If you recall, with statics, a resting object experiences a zero acceleration, so the right-hand side of Newton's second law essentially collapses to zero. So our approach here is we draw a free body diagram, we put labels on all of our forces, and we also have to draw a second diagram called a kinetic diagram that I'll detail here on this slide. Of course, we have to have our coordinate system, so this is identical to what we had with our statics approach, and we apply Newton's second law as we did with the statics approach. The difference here, when we took a statics approach, we referred to the equations as the equations of equilibrium. When we talk about a dynamic analysis, the exact same equations are now referred to as the equations of motion. So the only difference here is a change in the name. We move from equations of equilibrium for statics to equations of motion for a dynamic situation. And then once we have those equations all established, then we solve for all the unknown forces and directions, or we solve for unknown kinematic variables, and we'll illustrate that here in this lecture. So up here in the top right hand corner, we always have to put our coordinate system. Without a coordinate system, we would have no guidance on how to interpret all of our diagrams. Okay, so the governing equation, the governing principle for everything we do here, once again, is Newton's second law, where we add up all the forces that are acting on a system, and that's going to equal the inertia of that system times the acceleration generated from the net effect of all of those forces. And so we separate the equation to a left-hand side and a right-hand side, and by starting on the left-hand side, we begin with what we've done before, and we draw a free body diagram. Now, if we take a look at the system here, we should recognize that this is a box sitting on a flat surface, and so we have no indication that this is a rotating system. So this box is going to experience linear motion only. Therefore we'll only focus on the linear expression of Newton's second law. So starting with our free body diagram, we know that the box has mass, therefore will be influenced by the force of gravity, and we draw that force vector through the estimated center of mass. And because this is a box of uniform material distribution and a particle type that we can reasonably estimate, the center of mass is right in the middle. Because the box is in contact with a flat surface, Newton's third law is at play here, where the ground or the surface exerts a force that is opposite in direction and equal in magnitude to the weight of the box. And we'll label that as the ground reaction force or the normal force. So we'll use both terms, as I indicated on an earlier module, interchangeably. And so that's the first thing you should recognize when drawing a free body diagram with an object with mass. Now, what you need to wait for are the conditions that box is subjected to. So in this situation, I'm adding a force applied on the box, and this force has a particular direction, as you can see by the vector. I'm going to add a second force acting at this part of the box, and I'm going to add a third force. This could be a rope or a wire tied to this part of the box and applying a force in the positive x direction. Now, what we should also recognize is that because of the nature of contact between the box and the surface, there's going to be a friction force that's going to be a reactive type of force to F3, the horizontal component of F1, and the horizontal, or rather the F2, because it is perfectly directed horizontally. Now, one more thing I would like to add here is that with F1, we would need to decompose F1 into an F1x and an F1y, and the F1y would add value to the magnitude of FGRF. So before F1 was added, FGRF would have a value equal to that of W, but now that we have applied F1 at an angle, the Y component would add to the value of the ground reaction force. So that would end the free body diagram on the left-hand side, but now we know that this is a dynamic situation because you were told it's a dynamic situation. We then have to complete the kinematic side of the equation and the situation, so we need a second diagram. And so the second diagram is referred to as a kinetic diagram. Now this is a little bit strange because we're dealing with the kinematic side, but kinetic is a term that refers to that has a meaning of movement. And so when these equations and this approach was established many years ago, it was thought that, well, let's draw a diagram that reflects the motion of the object, to which the term kinetic refers to. But the kinetic diagram is actually depicting a kinematic variable. And so in this case, we would draw a vector centered at the center of mass, as we see with the weight vector and the ground reaction forces going through the center of mass, except that this vector is not a force vector. This is a kinematic vector. And this is a vector depicting the direction in which that object is accelerating. And so acceleration is a vector quantity, and its value is a multiple of the inertia of the box, the mass of the box. And so we would label this as MA. Okay, so a little bit on friction, because we're dealing with objects in contact with an external surface. When we talk about friction, it's also referred to as a shear force. So friction and shear are terms used interchangeably. Both refer to forces that are exerted parallel to a surface. So recall that forces at a right angle or perpendicular to a surface are referred to as normal forces. And there are two types of friction. The first type of friction that we'll deal with here in this lecture and in other applications in the course is dry friction. It's important to note that there is a type of friction referred to as fluid friction, which occurs between layers of fluid that move at different velocities. And this is typical inside the cardiovascular system, and is something that we'll address in a later module, specifically on tissue mechanics and a physiological process called mechanotransduction. But coming back to dry friction, there are two types of dry friction. There's what's referred to as static dry friction, in which there is no movement, no sliding of an object against the surface, and dynamic, or more commonly referred to as kinetic friction. And that's the friction between two surfaces during the course of the object moving along, or rather sliding along a surface. So if we take a look at the situation here on the bottom left of the slide, here we see a runner in the set position for, in this case, it looks like running a 100-meter dash. And this person in this position is not moving because the starter's pistol didn't go off yet. But being in a static position, this athlete is able to do that because of the friction between his fingers and the track. And so the track is exerting a force in the direction towards the left, because his body weight through his arms, through his fingers, are pushing on the ground. And because of the nature of the materials of his skin on his fingertips and the material used to make this track, the friction, the nature of the surface is such that his fingers will not slide along that track. And so this is not a complete free body diagram if we were to draw a complete free body diagram, of course, we'd have to draw a vector representing his weight. We'd have vertical components. We'd have components against his feet. But in this picture, I'm only illustrating the friction components. Now, on the right-hand side, here we see an athlete pushing a sled. So, of course, the athlete is applying force against the ground. The ground is pushing back, and he's applying force at the handles, and the slide is moving, but the slide is moving against the grass, which is applying a reactionary force that is opposite to what the athlete is applying against the sled. And so on the left-hand side, here we see an example of what we would refer to as static friction, no movement, and dynamic or kinetic friction on the right-hand side. So in terms of the of friction, there are three basic properties of friction that governs what is happening. So if the object does not move, the friction force, the reactionary force, is going to equal the applied force, and that's going to abide by Newton's third law of action, reaction, equal and opposite. So the friction force will be responsive in terms of its magnitude to the magnitude of the applied force. Apply a little bit of force, you get a little bit of friction force. Apply a lot of force, you get a lot more friction force. The second property is that every surface interaction has a maximum friction force. So if you're attempting to slide an object against that is sitting on some sort of surface, a table, the ground or the table will exert a force that is attempting to prevent the motion, but there is going to be a limit to that. And that's what's referred to as the maximum static friction force that a surface is capable of applying. And that's going to be a function of the normal force exerted by the surface against the object, which is responsive primarily to the weight of the object, but is also responsive to any other vertical force applied to the surface through the object. And it's also going to be a function of the coefficient of static friction. And so the coefficient of static friction is something that characterizes the nature of the contact and the structure, the materials of both surfaces. Now, the third property is that once the object is in motion, the force that resists the sliding will dramatically decrease and become less than what was experienced by the object from the surface in terms of its maximum static force. And this equation is going to equal once again, the normal force, so that's still going to be a factor here, but now we have a coefficient of kinetic friction, which is going to be less than the coefficient of the maximum static friction in most cases. And because Fn is going to be the same, that's not going to change, but because the mu, the coefficient of friction, is going to change by nature of the molecular interactions between the two surfaces, the resistive force exerted by the opposites, by the surface, is going to be different, and in most cases will decrease. And so in terms of estimating mu, we can calculate it with some of these data here, but essentially this has to be determined experimentally in a laboratory situation. What we see on the bottom table here are different material combinations, unique conditions to those material combinations, and the experimentally determined coefficients of both static and kinetic friction. So what we see here, if we have a brass object sliding across a steel surface, and it's important to note that the steel surface is clean and it's dry, the coefficient of static friction is 0.51. So before that brass object starts to slide, its resistive force is going to be in part a function of that coefficient of 0.51. Now, if you exert enough force against that brass object that it starts to move, the resistive force preventing that sliding will decrease, in part because the coefficient will decrease. And so the nature of the molecular interactions between the portions of the brass object and the surface molecules of that steel surface will alter in that less resistance will be applied to that sliding. So we see with steel on steel, the surface has to be clean and dry. We see the static coefficient is 0.65, the kinetic coefficient is 0.42, and we'll work through an example changing the static coefficient to a kinetic coefficient once we start the steel object moving. One last example here. If we have ice sliding on ice, I have a slight typo in the notes that I provided you, and so it's important to know that we're talking about a condition of negative 12 degrees Celsius. The notes that I provided to you, I was missing the negative sign, because of course if it's 12 degrees, positive 12 degrees Celsius, that's a great day to go out for a walk, because there's no danger of slipping on ice on the sidewalk. Water does not exist as a solid object at positive 12 degrees, but it does exist as a solid object at negative 12 degrees. So what we see here is that if we have a relatively smooth ice surface on top of another relatively smooth ice surface, the coefficient of static friction is much lower than that of steel on steel and brass on steel. So the resistive force to sliding is going to be much, much lower. Now, once that block of ice gets moving on an ice surface, you see that the coefficient of kinetic friction drops by 1 full order of magnitude. So once that ice starts moving on ice, it takes very, very little force to continue that block of ice to move. And so what we're going to do at this point, I'm going to stop this video and we'll start the next one at explaining graphically the difference between static friction and kinetic friction.